I would like to, first of all, thank my co-authors, Mr. George Way and Dr. Camille Kalouche, who both are giants in this field and in the field of asphalt rubber, and they're superstars of asphalt rubber. My talk and presentation is about noise issues and related to asphalt rubber. Obviously, noise issues are not new. It goes back way to 5000 BC, and appears that the very first noise regulation was 44 BC during Julius Caesar's era, that he forbid the wagon wheel into the city of Rome during the daytime because of the noise, and all commerce had to be done during, after hours, nighttime. And there are also numerous reports about the London report, and the very first indication of use of wooden blocks is an indication that somehow we resorted to some sort of surface, pavement surface, which was wooden blocks, to somehow mitigate the noise. And the very first pneumatic tires invented in 1888, and in the early 1900s, with the advent of automobile and rubber tires, it appeared that we somehow took care of the noise, and noise went away. And as more and more cars and automobiles, we built more highways, more and more noise got generated, and somehow this problem came back to us again. So we're going back to the very same issue that we thought we solved. And this is a typical indoor-outdoor noise, a typical unit of measurements for noise are in decibel levels. Typically in the 30 to 40 decibel levels, this is considered to be a quiet, tranquil setting. Anything from that to a noisy environment would be considered above 50 to 60. Typical highway noise that we consider are in the 60 to 90, and the threshold of the pain is at 140 decibels, and these are some of the indoor and outdoor noise decibels. This picture, pretty much this graph shows it a little bit better. The threshold of hearing noise, 0 decibel, is like, it really does not mean no noise. It is the very minimum hearing threshold. Like I said, conversation and a kind of a quiet setting is around 30 to 40. In the 80 to 40, 140 decibel levels is considered discomfort. And 60 to 90 decibels are like a highway noise that I'll be going to talk about it later on. We have typically 3 ways of measuring noise. The first is what we call it the wayside or far side. This is a noise meter at 50 feet or about 15 meters away from the center of the lane and 5 feet above. The standard is the noise meter mounted on a tripod. The cost is like the least expensive is about $600, the cost of this way of measuring. There are 2 other noise measurements. There's called close proximity near field. That is, the noise is being measured very, close to the noise tire and pavement measurement, very close to the tire pavement. And the other one is noise intensity. These both are kind of a research-oriented. The trailer or close proximity is about $40,000 to $50,000, and noise intensity level is 60,000 and up. This is a close-up of ADOT ISO CPX trailer noise. And this is the noise intensity. The other measurement of noise, these are two probes mounted on a tire that ADOT has adopted from Caltrans and GM, and these are like, looks like there are two probes, and each probe there are like two microphones on each one, so altogether there are like 4 microphones mounted on a tire that measures the noise in one pass versus 2 passes. So we have a little bit tweaked this noise intensity. And the wayside noise measurement is like, this is an indication of if a person is 50 feet away from the source of the noise, that would produce a noise of 67 decibel noise, and this is how it looks like. Now, if we somehow change the surface of the pavement, and that would reduce the pavement, even only by 3 decibels, that would how it would sound. And that is a huge difference. Only a reduction of 3 decibels, it's as if we have moved the noise source from 50 to 100 feet. So in a sense, a reduction of 3 decibels means that we have doubled the distance from the source of the noise away to 100 feet. And another rule of thumb is typically 1 decibel in noise reduction is it's like 2 feet of wall height. And as we know, one of the ways of measure noise mitigation is sound wall and berms. And sound walls and berms are effective in some ways, but they are very expensive. And in some of the applications, they are not really effective because in order to be effective, we need to have the line of sight broken. In other words, we have to have an obstruction. And in a lot of situations, the house or it could be up above on a hill, so the sound walls is not only is expensive, in some cases it could be not effective at all because of we're dealing with a situation that we need to have the line of sight to be broken in order to be effective. So sometimes it cannot be effective even with the most expensive sound wall. In highway noise that we are talking about, there are 3 sources of noise that is generated by highway noise. The 3 sources are the exhaust, tailpipe, the engine, and then the tire pavement noise. And for the most part, exhaust and engine parts are auto engineers somehow at the source. They can somehow control that by muffling or dampening the noise. But the main source of the most highway noise is generated at the tire pavement interface, and that is comprise about 70% or more of the noise in the highways. And at 35 miles per hour, that's where the tire pavement noise dominate. And on a typical freeway speed of 50 miles per hour or more, that compromise 75% or more of the highway noise that is generated at the tire pavement interface. So it's a huge contribution of noise through tire pavement interface. And ADOT has done some measurement through the CPX trailer noise that at the tire pavement interface and both at 15-meter wayside. And these are some typical numbers and measurements. For a random transfers timed concrete. The tire pavement CPX is 104.9 decibels. For transfers timed concrete is 102.5. For a longitudinally timed is 99.1. For a whisper grind, which is the quietest concrete, is 95.5. And for an AR rubberized friction course is 91.8. As you can see, there's a huge difference from 91.8, which is a rubberized friction course, versus the loudest random transfer tires, which is 104.9. By the same token, if we take noise measurement at the wayside, the same kind of a pattern is existing, because again, the same thing, if you took it at wayside measurement, is 81.1 for random, 78.7 for transfers, 75.3 for longitudinal, for whisper gun 71.7, and again for AR HDFC is 68. So it's a huge difference in decibels in both CPX noise measurements and wayside noise measurements. This is a typical, the very downtown Phoenix area is I-17 that we placed 1 inch of AR HDFC on. As you can see from the pictures, it's a course taken that is like 15 inches, 14 inches of concrete. We placed 1 inches of asphalt upper open graded friction course, and we noticed a decibel reduction of 3 to 6 decibels. The next project that we did was US 60 ADOT, that is a 10 miles segment of freeway on US 60 that we did in 2000, 2001, that the intent was to widen the freeway from the existing 3-lane PCCP in each direction to 6-lane in each direction. It was a 10-mile segment that included bridges and widening and sound walls. And as a last surface, we placed a 1 inch, which is 25 millimeter of AR HDFC friction course on the surface. And the idea at the time was, the placing of AR HDFC was to improve the skid resistance, improve the ride quality, and it was providing a very sharp contrast as far as striping. And the noise reduction was really like one of the side benefits that we thought at the time. And when we took the wayside noise measurement at different locations, at the shoulder, at the sound wall, and in the residential area, this is the before and after. Before we placed the AR HDFC on concrete, we noticed the measurement of 79.8, 76.6, and 71.7. However, after we placed the 1 inch overlay on concrete, the decibel definitely dropped to 72.6, 67.1, and 45.6 reduction. And as you can see, that was a noise reduction of 7.2, 9.5, and 6.1 decibel credit or reductions that we got. And that led us to a quiet payment program that I'm going to talk about in the next few slides. And before I do that, I would also like to mention the Phoenix area and the Arizona population. And as you can see from this chart, population growth of Arizona is humongous. Phoenix currently is like the 5th city, the largest city in the United States, and is rapidly growing. From this chart, it looks like in the past 5 decades, every 20 years or so, the population has doubled and is continuing to grow, and it's rapidly growing, and that growth, especially in the Phoenix area and its surrounding cities, is placing a huge burden on the transportation system. And this is the Phoenix area Valley freeways, what we call them. It's comprised of about 120 to 30 miles of concrete freeways that we built back as a result of Proposition 300 back in 20 years ago, and we're pretty much near completion of that 120 miles freeway. And this is comprised of Interstate 10, 17, Loop 101, 202, and 303. And because of this, we had to, because of the population growth and huge bringing of traffic and noise, we had to do something with the noise. And that, as a result of the previous project that we did on US 60, placing 1-inch ARAC FC on the concrete, that brought a huge success because that caused the citizens in the neighborhood to notice the quietness of the freeways, and they petitioned our governor at the time, and we came up with the Quiet Payment Program in 2003. So that's how Quiet Payment Program was born in 2003. Started in 2003, roughly about 1,200 lane miles of Phoenix urban freeways, which is concrete. We placed 1-inch ARFC over on PCCP. It's about $40,000 program. And since 2003 that we started this program, we have overlaid about 800 lane miles of roads and bridges surfaces with 1-inch overlay, about 1,700,000 tires recycled. The roads are definitely been silenced. Citizens are very, very pleased with the quieter freeways, and ADOT has enjoyed a national, international reputation. These are some photos. This is the very first project of US 60, that 10-mile segment is called I-10 to Val Vista that we did in 2003. And as a result of this project, as you can see, the concrete has been overlaid with 1-inch, what they call them, quiet pavement or rubberized pavement overlay. And this was how the Quiet Payment Program was born, because of this project, basically. And these are some subsequent freeway projects that we did after that. This is Loop 101 Scottsdale area. This is Interstate 17 Phoenix Metro area, May 2005. And the most recent one is just like last week. This is I-10 Phoenix to LA freeway. That is like a huge truck traffic and in excess of 150,000 ADT daily. As you can see, 1-inch of overlay on top of concrete, very quiet. The residents really love this product. This is again some other pictures of the freeway. I-10 Phoenix to LA freeway, 75th Avenue to Dysart, just last week. And this is another very important slide that is concrete versus AR ACFC. This is Arizona 101, Highway 101, that is a wayside. Is a concrete versus AR ACFC before and after. And as you can see, there's a huge difference in decibel. It is also very important to notice that between 1,000 to 2,000 hertz, there's a huge tonal spike or attenuation of a concrete versus AR ACFC. That is in that range of 1,000 to 2,000. The noise is very sensitive. The hearings in this range is very, that noise level at frequency is very irritating to human ears, and that is the tonal spike, as you can see, concrete versus AR-ACFC. Not only AR-ACFC is quieter, but in this range is also less it causes less irritation to the ears. And this is a combination of California and Arizona highways. This is a noise intensity. As you can see again, different surfaces of AR-ACFC versus concrete is a huge decrease in decibel between the two surfaces. This is a comparison of the same previous slide in a table format. Again, a big decrease. This slide shows the noise level at Park Tunnel that Dr. Camille Kalouche talked about it on Wednesday. That was his tire wear emission as the presentation, but this also shows that when the noise meter was placed inside the tunnel, at the exit, and inside the vehicle, this is how it's huge difference in before and after overlay of the with AR-ACFC. I also like to show you this slide, the noise meter slide. It's a big difference driving over concrete surface than going over AR-ACFC, overlaid, and then back to concrete. In summary, AR-ACFC reduces highway noise. Noise should be managed just like friction, roughness, rotting, and cracking. It's a quality of life issue. And this is where you can find more information about the Quiet Pavement Program, Arizona Quiet Pavement Program, and ADOT Ask for Rover projects. These are the two websites.
Thank you very much. As you can see, I'm the worst moderator for all the sessions because I let my speakers go all over time.
Ollie, I had a question about the measurements taken on the videos portion you just showed. What kind of a vehicle was that was driving, and whoever was taking the measurements, was that a specially equipped vehicle, normal vehicle, inside a bus?
No, I believe it was just a regular vehicle with some basically noise meter inside the vehicle, and that was where it was taken, right? It was a trailer? Yes. Okay, right by the car, yes.
I have a comment on a question. My understanding that sound walls, that actually the top of the sound wall bends the sound back towards the ground. Went through a conference, and so that actually line of sight is not necessarily a total consideration in the process. A question is one of the big issues we have with this in our area is the life of the pavement and the life of the sound reduction. Can you comment on that?
The life of the pavement, you mean the overlay, we expect about 10 to 12 years at least for the pavement. And I think studies shows that, numerous studies shows that, I think people have this misconception that over time the noise, basically properties, noise mitigation properties of AR-ACFC kind of goes away, but numerous studies has shows that very little, or if anything, as far as the noise properties, noise mitigation go away. And as far as the life of the pavement, we expect about 10 to 12 years of service. We have numerous projects that we have done that is even exceeded that 10 to 12 years, 15 years. And then we go back after, say, 10 to 12 years, mill off that 1 inch, and if the concrete needs to be basically fixed, maybe the joints, or do some prep, and put another overlay on it after 10, 15 years.
This is kind of one of maybe two-part question. Did you find the effects of the gradation and reduction of noise greater than the type of binder used? And what gradations were you using, and have you seen a change in effect if you were to run on the fine side of your gradation or the coarse side of your gradation?
This is really like a typical AR-ACFC mixed design. Gradation is the same, is like the maximum 3/8 of an inch size. The binder is regular. There's not really any specific design that we did for the overlay. It's a normal AR-ACFC. Even if we were to go and someone ask us to go and do the AR-ACFC design for noise reduction, we can't do it because there's not a science yet to do any tweaking or anything to do it any differently. This is just by whatever reason it is that that property of AR-ACFC being a open graded, maybe higher air voids, higher percentage of binder in it, that somehow causes the kind of a noise reduction as far as the mitigation measurements. There's no particular thing we do to the AR-ACFC itself.
Interesting paper that was given at AAPT that the Belgians had done determined that an optimum gradation of a 1/4 inch aggregate at 1.5 inch thickness with 22% voids was their maximum noise reduction. An interesting paper, and I'd be happy to share it with you there.
My perspective is a little different on that. We happen to have the lowest noise reduction in asphalt rubber layers because they are the softest of all the surfaces that we can put in a pavement, and it's durable.